Hey, hello everyone. Welcome back to our class. So this is going to be our lecture 3. There has been some shuffling, so let's convert it to 3. And this is going to be sort of a introduction to what makes machine learning different from just fitting a curve to your data, right? Why is it machine learning? There's some common concept that is taken into consideration, especially with respect to supervised machine learning. It's called generalization, and whenever you use different techniques in supervised machine learning, like the popular techniques like neural networks or deep learning based architectures for supervised stuff or support vector machines, etc., we need to take care of making sure we're not overfitting or underfitting. So these are kind of new concepts. So what is overfitting, what is underfitting, what is generalization, etc. And there's some, this is more of a methodology and a little bit of theory, not too much math, but more of methodology. Like when you're given a technique with different choice of parameters and a given data set, how do you make sure you use your technique optimally in alignment to the data set that you are working on? Because you don't use, even if it's the same technique that you're applying on 2 different data sets, you don't use it exactly the same way, although the methodology is the same. But the way you use NSVM on a dataset 1 is kind of different from how you would use it on a dataset 2. Only thing common is the methodology, so we want to focus on the methodology of the aspects, the pipeline today a little bit. And in lecture 4, we're going to start covering some advanced techniques like random forests and support vector machines, etc. Because we've gone through naive-Bayes and linear regression already on the basic side of the techniques. All right, so this is just a little cartoonish kind of a puzzle kind of thing, just for a little motivation. This is nothing to do with machine learning in general. Okay, say you had a knapsack, a sack of coins, and say it had copper and gold coins, right? And say the total number of coins in your bag was fixed, but there was a large set of coins in your bag. It's a very large bag. Say you're doing a capture-recapture, which means you're taking out, you're counting how many gold you got, or what is the proportion of copper and what is the proportion of gold every time in one count that you take. So basically you put your hand in and take out whatever comes out, you count and you put it back again. So again, you recapture. So you're not putting whatever you're counting outside the bag, you're putting it inside. Think of it like if you had a large sample, think you're looking at a huge lake, for example. You had a large lake of water and it has different kinds of fish, and you want to estimate the proportion of each kinds of fish, right? How many goldfish do you have in it? What kind of fish? How many salmon, etc. So you cannot take all the fish out of your lake and put it outside and then count. It's not possible. So you take out, you do some again, you take out, do some estimation, put it back. So the question is, what is the proportion of gold coins, which is why you're doing the capture-recapture. So the other scenario is even more difficult. Again, you have a large sample, but the total number of coins is variable. This is what happens in a lake, right? Fish die. I mean, fish die and new fish are born, and some fish die. So there's a variability in the true answer. So here your target is moving. It's not a fixed target. So it makes it even harder to estimate the proportion of gold coins. So the data sets, why have I put this kind of seemingly disconnected example here in a machine learning class. So you can assume that your data set is a sample that is coming from some distribution with some fixed parameters. You can also assume your data set is a sample that is coming from a distribution of varying parameters. So it's easy. This is more like a stationary situation. Stuff is like stationary, at least in what is generating your data set. Here that is changing as well. So both happen in real life. Although we sometimes assume that we're in this kind of situation when we're applying our techniques, it might happen that your training set is coming from a fixed kind of a population. You've done everything with that and you created your model. And then when you deploy your model in the company or in the academia or in your business, things might happen that the data set is not looking similar to what you trained on. Maybe a different kind of a data set is coming in the same situation. So we need to be aware of this. It's called this effect is called the covariate shift. So basically your features that you trained on have begun to shift. The behavior has begun to change a little bit. So this happens in real life. So it's good to be aware of it. All right. So this is now it's more formal, more relevant. So standard notation, we've looked at it before. Let's assume X is used to denote the features or the predictors, right, which is the input variables. The Y is denoting the labels of the responses. You have n samples of X comma Y that is given to you in a regression or a classification setting. The X has, say, P features, and Y, until now we've been studying Y to be only one vector of labels or one vector of response variables in regression or labels in classification, but it might as well happen that you're trying to predict multiple columns in some settings. So we always keep discussing the email example. Say you had a bunch of emails and a lot of data that you collected from it, that would be your features. Your labels would be you're trying to classify whether the email is spam or no spam. But if you want to classify more than one column of spam, other than spam or no spam, if you want to classify the email or some other category as well, like say official or personal, or like Gmail these days is creating smarter inboxes where it automatically classifies promotional emails in a separate tab, standard emails in your primary tab. There is a like social network related emails in a social tab. So that's another classification. So every email is to be either classified as both columns. So there your case 2, for example. The first column has only 2 possibilities, spam, no spam. The second column has maybe 4 possibilities. So that's another situation there. Okay, so we discussed this. This is more for a recap since Gauss created and thought and worked out the linear regression setup, which is this. You're trying to minimize sum of squares. That's what the norm, this thing, these 2 lines and 2 is denoting sum of squares of the error between your response and the straight line that you're fitting using the betas that you're learning, which is the coefficients of your straight line or your straight surface, straight plane, hyperplane. Then we went on to generalized linear models, which is a special case of this. But there's something called generalized additive models, which is interesting, where for each individual, so your sigma is running on one column at a time, and you're fitting a function fi of xi. So if you had 3 variables as input, 3 features, you're fitting 3 different functions, 3 individual functions, and you sum up those 3 functions, and then and then you get your final prediction. But what is G-inverse? This is similar to what we studied in GLM. In GLM or in GAM, you take a distribution assumption that your response is distributed according to some distribution. So, and you're trying to predict the expectation of the response. So basically, yi may be distributed as normal with mean 0, variance 1. Y2, the second record, may be distributed as mean as well, so again a normal with a different mean and a variance, etc. So you're trying to predict the mean. You're fitting a distribution to each output, and you're trying to predict the mean of that distribution that you're trying to use to model as your output prediction. So G-inverse is just a technical aspect of it. It's trying to match the domain that a mean can take for any distribution. So Poisson mean, if you took yi as Poisson, expectation is always supposed to be positive, so G-inverse would be exponential. So there is a pair for any chosen distribution. There is a specific G-inverse function that you're just doing to match your distribution assumptions. But the main part of the fit is happening here. Here the idea is, if you see in linear regression, you're fitting x1 beta 1 plus x2 beta 2, so it could be f1. x2 beta 2 could be decided as f2 of x2, right? But it's a simple function. But here I'm saying fi is not necessarily linear. It could be a nonlinear function. So let me show some graphics. So say you had 4 input features. This could be the f1 of x1 that I fit. This is f2 of x2. This is f3 of x2 of x2. This is f3 of x3, f4, x4. So to get my final prediction in my y, all I need to do is I need to add up these 4 nonlinear functions. So there's a sigma. I'm adding up 4 nonlinear functions. So say if someone says that this variable, when it is 0.2, then f1 of 0.2 plus f2 of 0.2 plus f3 of 0.2 which is a bigger number, plus f4 of 0.2, which is 0 in this case, will give you the prediction of what is y supposed to be for an input of 0.2, etc. Or you could look at it in other combinations as well, but you know that you're adding up functions. Okay. So at a high level, all we're doing is we're finding a map that goes from input features to your response variable, and that map might have parameters that you're supposed to learn to get a proper map so that your prediction is being done properly, or classification. So what is the example of parameters in the case of linear regression? It is beta. Your map is x beta, but your parameter is beta that you're supposed to learn, because x is known to you, beta is the unknown parameter. Here your unknown parameter is the function fi, right, which might again have other parameters, but fi's are the unknowns, xi is known. Supervised learning, we've seen this before a little bit in the first class, so it's kind of when we discuss different paradigms of machine learning, like supervised, unsupervised, etc. So here we have the setup is basically you have a set of features x, you have a set of known labels corresponding to those features. So this is a training set. I gave you emails and some labels corresponding to those emails as being spam or no spam. You use that data set as your data set, right? Your toy data set, your input data set, your working data set, and you learn a function that goes from x to y, which is the learning function, which is f. And to make sure your function is good, there is some loss function that you're using, some objective that you're trying to maximize or minimize. Right, like in least square, in regression, it's the least squares objective of minimizing the residual, etc. So that's the setup. But then the thing is, you have a function that you learned. So this could be your support vector machine or neural network that you learned, or linear regression that you learned. Then you apply it in your business or in your real life, right? That's the reason you learned this mapping, in research or business, whatever it be, the reason to use it, right, or in industry, etc. So when you apply it, the situation is you would not know what the labels are. And when you're training, in the future, you would only have features available, but at the point of training, you don't know when you deploy it what the test data set, what is the data that will start flowing into your function. You won't know at the point of training. You will only know when you really deploy it, then this becomes available. But this is unknown forever. Whatever you're predicting is all that you know. You don't have a ground truth to compare whether what you're predicting is matching what it is supposed to be. So this is why this is the supervised learning setup. If I only was talking about this part, then it is just curve fitting. As long as I can go from here to here with some f, I'm fine. The learning part is this. You want to learn a function that does not necessarily just good here, but mainly it needs to perform well in terms of its prediction in the future, where features will become unavailable when you start deploying it, but label variables will never be known. So you will never know whether you're doing a good prediction or not. So say you're trying to predict something in your industry, whatever you're predicting is what the company needs to use. It doesn't know whether you're doing a good job or not. So how do we evaluate? This is the last function we care about. Here, we care about the quality of prediction here, because this is what is impacting the industry. This is just in your lab, in your office, in your cabin. So is there something we can do in this kind of a setup where while training itself, we can make sure that we are building a function that will perform well in this seemingly difficult situation? Because that's what you want. You need some guarantee that it is predicting well in this situation. What can we do? So that's the learning part of the thing. So there is something that we can do about this. So we're going to learn that in this class, actually. That's the point. So the title of this lecture was starting with generalization in supervised machine learning. So the point of generalization is referring to the situation. You want to build a function on your available data set so that it generalizes to future unknown data in a good way. Okay, so we talked about loss functions that we are using to quantify the error in how well your prediction is approximating the truth, right? So if f theta of x was your prediction that goes from x to y, you're comparing how f theta of x and y are matching using some loss function L, right? In linear regression, the loss function was this. You're subtracting and adding up the sum of squares. There's a sigma here if you want. But there could be other loss functions as well. But the point is the loss function depends on a parameter theta. So now if you use a bad, not just the loss function, sorry, well, the loss function does depend on your parameter theta, but mainly the map you're learning depends on a parameter theta. So as a result of it, if you put in very bad thetas, so in linear regression case, thetas are your betas, right? If you put in very bad coefficients, it's not going to predict. It's going to give you some result out, but it's like garbage in, garbage out. Or like good data in and garbage out in terms of your prediction. It's not going to match the y's anyway. So in a way, your loss function needs to be evaluated with respect to the thetas. So you need to choose the thetas or the betas such that your loss function is minimum. So your loss function is with respect to your theta, with respect to your unknown, because x and y is known anyway. Now what's going to happen? Say I give you these black circles is your data set. Let's say it was a 2D data set. So x-axis is one feature, y-axis is feature number 2. This is x1, x2. You have 2 features. And then say, oh, let's think of it differently actually. Yeah, these are 2 features and your dots are your response variables. So you need to learn a map that goes through these dots as good as possible. But then it'll be difficult to visualize. You know what? I'll take my word back. Let's call this, let's keep this simple. Let's think of this as x versus y, okay? You only have one feature, okay? Your x-axis is your input feature variable. Your output is your y-axis that you're trying to predict in a regression setting. So then it matches perfectly. So basically it says when x equal to 1, then your y happens to be somewhere around 0. When your x is equal to 0.2, your y happens to be somewhere between 0 and 0.5, somewhere here, 0.25, etc. So you want to learn a map that predicts this automatically, right? So there's different colored curves and lines in here, basically curves. If you see the violet curve, this one, the purple, it's trying to go through most points then in relation to other curves, right? It's trying to fit even more than it could. Of course, it missed a few, but it's trying to fit a lot more than the others. Then there is the black and then the blue. The blue is the next highest it's trying to fit. The black is the map, the f theta that is next highest, for example. And then green is a little more lighter. It's kind of missing a little more points than the others, a little more smoother. Then red is too light, right? It's missing a lot of points. It's just going through this overall pattern like this. It's not going through a lot of points. So red is not predicting a lot of points in a way. Yes.
Red, violet, different samples.
The colors are your function that you're learning. This is your machine learning function. This is your prediction function.
Oh, function.
Yeah. So this is x. X-axis is your input variable. Y-axis is your label. And this is the function. F of x may or may not pass through the label, right? So for your red function, f of x is not predicting all the y's it is supposed to predict. The violet function is f of x. This is x, so the violet is f of x. It is passing through a lot of labels.
Function means one is regression.
Sorry, can you say that again?
The different one is a regression, one is the other one.
So in this particular plot, I'm talking about regression function, not the classification, the regression function. So this one, right? So in linear regression, you have input variables x. So this is your x-axis in that picture. Y-axis is those circles or your labels. So y-axis is basically the labels as well as the circles, which is the same thing. This is the function that is different colors that you're seeing, that is trying to predict from x to y. These are different colors in a regression setting. Now, if you see, the point I'm trying to steer towards is the fact that there is many kinds of functions you can fit that go from x to y. Some will be much lighter. I could even fit a super dumb function that's like a straight line. It goes through only maybe a handful of points. It won't predict a lot of points. But your your red is little better than just a straight line. Now the question is, there's many functions you can fit. Here there's a handful of maybe about 5 functions that we've shown as examples. So which one is the best? Some people might say, since I'm able to predict everything using violet, maybe violet is a good function because I'm able to predict every point. Not true, because I will show in the future. Some people may say maybe violet is over predicting, maybe red is better. It may be true, it may not be true. So what is it that decides it? How do you choose this? And also, based on your choice of theta, you can decide how complicated a curve you're fitting like white, or how simpler a curve you're fitting like the red one. So now I'll show you a more extreme example. Same situation. I have only 2 curves, right? Not so many colors. This is one feature variable, x-axis. Y-axis is your label, which is your circles that you're trying to predict. Now, say I use 2 techniques. One technique fits like this, the green one. It goes through most points, but if you see, it goes through the overall pattern, but it doesn't go through every single point. Then there is this crazy technique I use, which is the red variable, red function. It is going through every single point in my curve. It is not skipping even a single point. So some people may say red is the one to go with. We will get 100% prediction error. It's like a crystal ball. Whatever input X you give me, I will predict Y exactly, correctly, 100% of the time. Some people may say maybe that is overfitting. Maybe green is better. So we need to understand how to choose which one is better. So this is the point of machine learning. So how do we generalize? So the goal here is not to choose a function that literally goes through every single point. In some cases you might need to, but the goal is not to minimize that prediction error. The goal is to minimize the prediction error with respect to your test set. This is your training data, but in your future, you don't know what your y-axis is. I will only give you variables coming on the x-axis. And then I need to use my function and believe that it is performing well in the future prediction setting when I deploy my model. That is the error we care about, not like 100% accuracy in here. We need 100% accuracy there when you deploy your model, not just data. Yes.
So here in this case, 2 functions, right? 2 functions means, can I consider that 2 are different algorithms? One is SVM approach and one is some regression. That is what you mean, or?
Yes, that is one way of thinking. That is definitely one perfect example. You can use SVM versus something else, linear regression, some neural network, for example. But also, there is another situation where only for one algorithm, say if you took SVM, you might have, SVM has parameters that you need to tune for it to work. Just like linear regression, you need to tell what the betas are to specify the entire linear regression function, the line. So SVM also has parameters, as we will see in the future. So basically, every function that you're learning has parameters, theta. Now, for the same technique, maybe f is always SVM, but for, say, the parameter equal to one set of values, you get one kind of a prediction, and then maybe the green one. But for, again, the same SVM, for another set of thetas, you get a red kind of a parameter. Now, the question is, which SVM do I use? Like, with which parameter set do I use for predicting well in the future, not necessarily just predicting well on my training data in my computer? So those are the 2 settings. All right, because SVM, and these are kind of powerful techniques, you can always try to find some parameter where SVM will start passing through everything. SVR, because this is a regression, support vector regression technique, will pass through almost every single point on your training data, and you might get 100% prediction error and 0 error as a 100% prediction accuracy on your training data for one set of parameters for SVM. Then another set of parameters might have maybe 80% accuracy or 90% accuracy, like the green line. It is passing overall the pattern, but it's not passing every single point. But which one is better? We don't know, because SVM with 100% accuracy on training data may have just 10% accuracy on the test data when you deploy in the future, but you don't know how to evaluate it.
In this example, how can we find out the error? So the red line is zigzag, right? So how we can...
So basically, the red line is going through every point, right? So f of x is the red line, and then y is your label, the circle. So f of x minus y every time is 0. You see the red line at this point is exactly equal to the label. If label was 0.7, f of x is also label 0.7 at this point. So f of x minus y whole square is 0, the least squares error. But in green, it is 0 at this point. Here the error is little away, so it is maybe 0.1 is the error. 0, 0, 0. Here the error is maybe 0.4, like that, or 0.2. So like that, I sum up all the errors for green versus sum up all the errors for red, sum of squares of errors. So red will have 0. It will literally go through every line, every point. Green might have maybe 80% error, 90% error, 95%, maybe 60%. Yeah. Like that. If I drew some line like this, just straight line as my prediction, it will maybe pass through 1 point or 2 points. So my error may be 98%, 95%, something like that, 99% error, because everything else.
Got it.
Yeah. Okay. So also error and accuracy are just analogous terms. So if error is 0, it means accuracy is 100%, like that. Just in other way around. Okay. Now the question is, how do we generalize for future data? That is, so how do we choose basically? So this is a setup. This is a little theory, but not too hard. So basically, the assumption in machine learning or statistical modeling is that your x and y come from a probability distribution that is unknown to you. But we assume that they both come from a joint distribution. So what is a joint distribution? A joint distribution is a distribution of more than one random, of 2 or more random variables, right? So a joint distribution, an example is the x could be the event of whether it rains or not. Y is the event of whether match gets cancelled or not. So then there is a joint distribution. If x equal to rains, then what is the probability of x equal to rains and y equal to match gets cancelled? What is the probability of x does not rain and y equal to match gets cancelled? Maybe some riot happened and someone put in some bomb, but that's a very unlikely scenario. But rain is slightly higher scenario, right? The joint. So there is some distribution of probabilities across all possibilities of x and y taken together in pair. So that is a joint distribution, like we studied in our probability refresher in our first lesson or two, maybe the second lesson. So we assume that x and y come from some unknown joint distribution. That's why there is some phenomena you're trying to mimic. There is some behavior, right? That is why you're trying to model like spam or no spam. Everything has some sort of distribution. Like some things are more likely, some kind of emails are not likely for spam. Some kinds of emails for no spam are more likely, and some kind of emails for no spam are unlikely, right? So a very spammy email that is not spam is very unlikely. Similarly, a very official, nice personal email, all kinds of emails that people usually have in a society are very likely within a no spam bucket. So this y can take two possibilities, spam, no spam. Then based on what kind of email you're putting in x and y, you have this kind of a x with y being spam is likely, this kind of x with y being spam, not spam is likely or unlikely, etc. You have all possibilities. So that is what we mean by XY joint distribution. Data has a distribution. And by distribution, I mean there is some sort of a probabilities that are being shared by all possible behaviors of x and y. Some are more likely, less likely. Now the goal is not just to minimize the loss function on the training data set, but to minimize the loss function in this setup. So this one I will show in the last equation, but in our training setup, all we have is we have a sample. You don't have you have the x's and y's, not the bold-faced ones here, is denoting the sample coming from this distribution. So you don't have like infinite, like you don't have like a trillion set of x's and y's. You only have a sample of 10,000, 100,000. If it is big data, maybe a few million, like in Facebook or some big company in pharma or whatever. But you have a sample. You don't have the true possibility for everything. You don't have the distribution that can generate the sample. You only have one sample of data. So in that setup, all we can do in terms of our loss function, it's known as empirical risk minimization. You choose some loss. It could be the sum of squares of error like we did before. And you're trying to minimize the average of that loss within your n samples that you're taking. Say you had n records of x and y. You're trying to minimize the average of that loss, which makes perfect sense, right? Because you don't want to minimize loss only at this point. You want to minimize loss at the average error at all the points. So you take the errors of all the points, write it in an Excel sheet, you take an average. Then you say, on average, I'm performing this well or this bad. That's what its equation is exactly showing. So empirical risk is the average expected loss on seen data, because this is your sample data that you have. But what we really want to optimize, so this is what we're optimizing for on the training set when we're trying to, so basically the red line here, this is that average loss is 0. Your accuracy is 100%. Your error is 0. The green line, your error may be some 90%, right? So this is what you're optimizing for when you're deciding whether red or green. So if you took this as your criteria, automatically the least error will be for the red line, because that is the one that will do better on this loss function than the green one. But is that the one we are hunting? Not necessarily. We are not hunting for just that. So what we are really looking for is minimizing the true risk minimization. What is true risk? True risk is the expected value, expected risk on the process generating the XY pairs. The process means the distribution generating. So, like, a joint distribution, every possibility of X and Y has a probability, right? That is P of XY. This is the joint distribution. This is the D. So you want to minimize X. This is an integral. It needs to be a double integral, actually, integral on X and Y. Or under the integral I put X comma Y, so that works as well. So so it's like a double for loop basically. There are two integrals here, one on X and one Y, which is what is denoted by this notation, integral with X. So all possible combinations, infinite combinations from negative infinity to infinity that X can take and as well as Y can take. All possible combinations in this double for loop kind of integration. You want to minimize the error. You want to minimize this error because some losses are more likely to be seen, some losses are unlikely. So if this was stock market data, a loss of $1 billion is unlikely to be seen every day. $1 million in the stock price is also unlikely to be seen, but sometimes it happens when there is a crash all across the world. There is so many stock transactions going on. If you sum everything up, on the whole, in the entire planet, maybe people lost $30 million today because the New York Stock Exchange, the Bombay Stock Exchange, Shanghai, whatever, crashed. So $100 is like very, very likely. It is very likely somebody in this world on average the loss maybe a lot more than, maybe $100 also less likely, because if we are making 1 billion transactions every day or 1 million transactions on the stock exchange, it's very likely that the average loss or the average gain is much more than $100, right? There's people that lose thousands of dollars every day. And same thing, the gain as well. They gain thousands of dollars. The average may not be like, hey, the entire planet gained $5 here from yesterday to today. Maybe they gained a few $1 million from yesterday to today, or lost something like that. So you're measuring everything with respect to the distribution, the integral, negative infinity to infinity. That's the integral going from one end to the other end, the limits. And you're minimizing whatever is, but it is being weighted by how likely it is also. So maybe it's just having a very high loss at some one particular point may not be very likely when you see across all the data set. So then you're downweighting that. But if that loss is very likely across all points, it's like the average error that people get, then P will be high. So it's like a weighted average, weighted sum that you're minimizing. And this is nothing but the expectation. We studied about expectation and variance in our probability concepts in the last classes. So this is the expectation of the loss basically, because loss is the distribution. You're taking a distribution. So basically, X and Y have a joint distribution P of XY. So any function of a random variable is also a random variable. That's a property. So L of f of x comma y is a function of x and y. So that also has a distribution, the same joint distribution P of xy. So here this is measuring integral of random variable times the probability, right? So joint random function times the probability of that joint random variables, and you're summing up. So this is integral x p of x kind of a thing, which is the formula of expectation. So this thing is nothing but expectation of the loss function. So you're minimizing the true expected loss, true expected risk. Risk is another word for loss. So that's what you're trying to minimize here. So this is what you need to aim for. Now the question is red minimizing this the most or green minimizing this the most? That's what we care about. This will, because whatever minimizes this will do the best in the future when you deploy your model in your real life. Minimizing this and giving 100% error is not necessarily going to do good in the future. It's not necessary. It might maybe in some situation. So another way, a cartoonish way of thinking about it is, so this is what machine learning is about. It's not about just fitting whatever curve fitting, making sure you fit a curve that goes every point is not. Make sure we fit the curve that goes through the right amount of points and makes the right amount of error so that in the future you are going to do good, better than what you did in the current state. Yeah. So that is the machine learning. Your choice of theta will decide whether you're fitting like red or green or something worse, like maybe something else. Now another thing here is another cartoonish example is this. So x and y from the true distribution, right? The true distribution is like the person who generates your exam question paper if you're studying for some examination, right? You don't know what kind of question papers are coming out. All you have is a set of question papers that people have generated. Say you're taking an exam this year, but maybe online or somewhere, you know what are the kinds of questions that came last year and until maybe last 20 years, you know what kind of questions came for that exam. But you don't know what will come in the future. So you only have a sample to prepare from. You also know what area, the distribution might be, say, the area, for example. Say you're giving a calculus exam. You know what your syllabus is, what is the area from which the XY is going to be generated. You might have maybe 10 books, and maybe your class is using 1 or 2 books as your textbooks or your main books, right? So all you can do is prepare from some sample from calculus. You cannot prepare every single thing possibly that can ever be asked in calculus, because that is not possible, because people can generate questions from calculus, like create new questions from the same concepts, right? So you can never have this be known to you. If you knew that everyone will pass with 100% marks in their examinations, that's not happening. All you have is a sample that you're studying through textbooks or whatever. So if I give you some test exams before the main exam for practice, and say, instead of you learning calculus, you literally memorized everything by heart. So for this particular question, the answer is 3. This question, the answer is 9 times x squared plus 5. You just learned it by heart. You just memorized it. What will happen in your performance on the empirical risk? You will get 100% marks. Here you will make 0 error. Now, can I tell that you're like Einstein, you're getting perfect everything, every time you're like a genius in math? Not necessarily, because when I give you exams coming from the distribution, the concepts of calculus, someone who memorized here will have 100% marks in here, and he'll get 0 marks here, because unless he gets the same question, which is very unlikely, if he gets that, even then he will get very low marks. Maybe 1 or 2 questions match that he exactly memorized, because he remembers the answer. Now, everything else, he has no idea of how to go from x to y. He has no idea about the f that he learned is very bad. So this is like the red function. You will get 100% marks on your practice exam. He has memorized everything. He's overfitting his data. He knows exactly for what x, what y will happen in a memory kind of a thing. But when you give him the right the test set, he will get 0 marks. So it is in that situation, this red is not necessarily good. It has good performance on your training data. So you might think, hey, I used SVM today on my company data set in my computer. I am getting 100% predictions. I'm doing an awesome job. Then you deploy it in the future, and you don't know how well you're doing, but the reality is maybe you're doing a 0% prediction properly. So that's the concept of generalization, and overfitting and underfitting. So maybe maybe the violet is overfitting, maybe red is underfitting. Maybe something like the green is doing better. You never know. So you need to figure out how much amount of fitting you need to do, which is the optimal fitting. Am I supposed to overly fit or underfit? What is the correct pattern in the middle somewhere between these two extremes? So underfitting could be like just drawing a straight line. Overfitting could be the red line. But somewhere in the middle lies the real gold, where you get the best prediction performance in your future data set. So that is the curve that is really learning all the concepts from going to X to Y, not just memorizing things. So yeah, I think this thing we can skip for now. Okay, so how do you decide the complexity of your fit? What am I denoting by complexity? I'm denoting how complicated a function I'm drawing, like this, or just something simpler. The only way you have some knobs in your hand when you're using these different techniques. Every technique has some knobs that decides the complexity of your fit. And those knobs are nothing but the parameters that the technique has. So if you're fitting a 2D linear function, something like linear regression or a linear hyperplane for a larger high dimensional data, all you can decide is what is the slope of my plane and what is my intercept, because beta naught is the intercept, beta 1, beta 2, all these are the coefficients, right, that decide the slope. Because a line can be written as y equal to mx plus c, or it can also be written as y equal to n, either way. You have these two parameters that decide the complexity of the fit. But unfortunately, linear functions are very simple functions. This is a function class of only linear functions. So whatever slope and intercept you do, you're still getting a linear function. So maybe in a data set like this, a linear function will do very bad. You can fit some line like this, some line like this, some line like this, but you can never do this curvature thing, right? So that is, here the issue is with respect to not just the choice of parameters, but maybe the choice of function class. So the technique that you picked may not be good enough as a whole. The best you can do in that technique is limited. Cubic spline. So this is another technique that can fit these kind of different curves, right? So in a cubic spline, basically, we are going to study these in the future, but it has these different parameters. So basically what you do in cubic spline is you fix that the function has to pass through some specific points that are known as knots, and you tell how many of those knots and what is the location of those knots that the function that you fit needs to pass through. The rest of the places, the function can do whatever it wants. It can do all kinds of wiggly, jiggly things, up and downs and everything. It can do nonlinear stuff, but as long as it passes through those specific points, then it's fine. That's a cubic spline. Nearest neighbor regression. You're trying to predict the future label based on looking at a future input data by looking at what is other input data that looks similar to your future input data, right? Based on your neighbor. Similar behavior, what is the response been? So maybe some average of that you can predict. That is nearest neighbor. Lasso is a linear regression with some constraints on your beta. We'll go through this in the future. Support vector machine, we'll go. These are separate classes, support vector machine, nanopod, lasso. But point here,
can you repeat the first two, please? I missed it.
These two, huh? Yeah.
First two.
Yeah, 2D linear function is basically linear regression, right? With two variables. So this is the y minus x beta that we were looking at. So there the only things that you need to decide is your coefficients beta. That decides the slope and the intercept of the line that you're fitting, right? So if you had a data set just like this patch, forget about all other points, say only had data set from these points to these points. So then this is a reasonably good straight line that is passing through all the data because you're fitting straight line. But if you fit a straight line for this data set that looks like this, then it's passing through maybe 1 or 2 points. The only decision on how weak of complexity of a straight line you're fitting or how strong complexity you're fitting is only decided based on your choice of slope and intercept. Because what is changing between this line and this line is the slope of the curve and then the intercept, right? Intercept is where it intersects with y-axis, and slope is how the slope is, which is the angle it is making with the x-axis, right? So this has slope 0. If I draw a parallel line, slope 0, and intercept at 0 as well if it passes through origin. If it passes through here, a straight line, then slope is 0, intercept is 0.5. But here the intercept is going to intersect somewhere here, so maybe at 2 or 3 on the y-axis, and the slope is like this, maybe some 45 degrees. So a line can be uniquely identified just by 2 parameters, slope and intercept. And what slope and intercept you choose will decide how well it will pass through your data, how well your prediction is. So those are the only parameters that can control what your line is. Everything else is known. You have an equation. The only unknowns are slope and intercept, basically. You have y equal to mx plus c. You need to know what m is, what is c. Similarly, cubic spline is another technique that needs a little more detail. But here, at high level, I'm just saying there are different techniques. Every technique has parameters. That's what my title is, parametric characterization of the mapping you're learning. So every technique has parameters. How you choose your parameters is where you need to use your machine learning correctly. You need to not overfit or underfit. You need to optimally fit so that in the future you're predicting well. So in the second technique, basically cubic spline, there is a concept of parameter called knots and number of knots and location of knots. So if I say I have a cubic spline with 3 knots, I'm saying I will give you 3 points through which my function has to pass, and I will tell you where those 3 points are, right? So I will say my function, whatever function I fit, has to pass through this point, and this point, I will say. So I can fit any function. It can do whatever it wants in the rest of the part of the space, but when it comes to these 3 points, it has to pass through this. So I'm giving it a lot more freedom, degree of freedom to move around. As in the choice of functions is much bigger than just choosing straight lines. So even the cubic spline might do better on this than a linear regression on this particular data set, for example. So if I say I'm choosing a 50 knots and I say 50 points, it needs to pass through everything, then I'm not giving it much movement because it needs to pass through those 50 very carefully. It needs to memorize those. And then the rest of the places it can generalize and do whatever it wants, like that. That kind of thing. So that is the cubic spline technique. These are different techniques in general, statistical modeling, machine learning, whatever you call it, math, whatever it is. So the point is different techniques, different parameters. Now machine learning is all about choosing parameters that not only minimize your training error, but mainly you don't care about training error as much as your test error. Test error is when you deploy it in the future data set, how your prediction is. How is the quality of accuracy of predictions there? That is what you want to optimize for, and you need to choose these parameters for any given technique that you use in a way that is minimized, which is your true risk. So let's see where our time is on. Yeah, we are on we are coming towards the end, so it's good. So how do we do that in practice? Now this is more practical stuff, right? How do you minimize the true expected risk, which is this one, right? The double integral of x, y, plus the whole distribution. You want to minimize the test error, the feature distribution, right? How do we minimize that? So there is a technique called cross-validation. There are different kinds of there is one called leave out, there is one called KFold cross-validation. So basically here the idea is you have a training data, this is the sample data that you have to work with to generate your model, but you need to make sure it performs well in the feature data. How people do that is in leave multiple out, say you had these many rows, every time you leave some amount of rows out as your validation data. So in this case, say you had m rows, you are going to take a subset of d rows randomly and put it aside, like here. You call it validation set. So the train and you only construct your model on the training set. Because now this guy, when you're trying to construct the model cannot see what this data set is. This is its exam. This is your textbook, right? You're preparing from. So you learn on this and then you're evaluated on the validation data set. So your predictions come out from your model. You compare what the predictions are by using this model to predict on this data set. So you take your data set, split it into two every time. One split you learn to train the model, then you have the model, then you predict with that model on the other split. So you try to predict what the output is supposed to be just by looking at input variables here, so that now you have a ground truth of what you are predicting and what it is supposed to be. So you can measure your error, your mean square, your squared error. So that way you can evaluate. So now you can do this for every single choice of parameter. So you can say if you want to fit support vector machines, it has some 2 parameters. You can try all possibilities of parameters by this process and you see which choice of parameters performs the best on the validation set. But you don't do this once. You take so first time maybe you take 1, 3, 6 out as your validation. You write down your error. Second time you take you put this 1, 3, 6 back, and second time you take some other d number of points out and put as validation. So you repeat again and again. So basically you're training it on something to study on and train on, and something to practice on, and see you're doing well on the outside, on the data set coming from the outside, from your test exam. So you're not telling it, look at the entire data, fit a model, then it's going to memorize everything if you want to minimize the error on the entire data set, because it knows the input, it also knows the output. Here it knows input, output for training, but for output it only knows input variables. It doesn't know what the output is. But what is even more popular, that is not in this, it is in this slide, but it's in the next slide, is another kind of cross-validation. This is what we would do day to day. It's known as KFold cross-validation. Here again what we are doing is, so what we do is say, okay, here let me tell you what this is. This rectangle, let's assume this is your entire data set. Okay, and any rectangle is your entire data set. What you do is, in KFold cross-validation, you choose a number k. Let's do say 3-fold cross-validation or 5-fold. But for example, let's say we are doing 3-fold cross-validation. What you do is you divide your data set into 3 chunks. So if you're doing 3-fold cross into k chunks, whatever k is, k could be 5 and 5 chunks. And then, so these are the different chunks. So there are a lot of dots here. It's saying that I've divided it into k number of chunks. And then one chunk in my first iteration, I will say is my testing chunk, is my validation set. I put it aside. I only use the rest of the data. So I use only this amount of x and y to train my data. Okay. And then I test on this and write down what my error is. Because here I know ground truth, but the model doesn't know the ground truth. It is really predicting just by looking at input x here. It is predicting what the y is supposed to be. You get an error. In the second pass, what you do is you leave another chunk out. The chunk that you left first time, you bring it back in into your data set. Now it is part of your training data, but you leave this chunk out now as the testing data. So you train on this and this data set, completed this part and this part put together, and then you test your model on this, you write down the error. You do that. Now next time you leave this chunk, then you write down error like that. In the end you leave the third chunk, fifth chunk, whatever, your kth chunk that you chose as your validation set. You train on all of this and you test on this and write down the error. You average all the errors that you got on each of these chunks. Every time you're leaving one fold out, this chunk is called a fold, basically. Fold, chunk, same thing. You average those errors. That is your prediction performance. Now, for SVM, you have whatever technique, say you have some parameters. Say your technique has 2 parameters. It could be SVM random. that parameter can take different values, right? SVM can take that parameter could be 3 for one, another parameter could be 5. You might have 7, 9, minus 5, 6. Whatever your parameter is, 0, 1. For every choice of some discrete possibilities of parameters, you do the entire KFold cross-validation. So one choice of parameters, you choose what numbers go into those parameters, you do entire KFold cross-validation, you write down error. Now, for again the parameter equal to 1, 3, I get a cross-validation error. The parameter equal to 5, 7, I get another cross-validation error. Parameters equal to 3 and 9, I get, so I try everything and then I choose that combination that gives me the least cross-validation error. So why is this a good idea? The cross-validation of whatever sort is a good idea because you're not giving it the entire data set to learn and memorize from. You're giving it a training data set to learn the concepts so that it will do better on the testing data set. That's what you're optimizing for when you're choosing the best parameter. So which is what we want. That is basically mimicking this behavior. Not this training error, but the test error that you're trying to minimize. So you're trying to find a model that has a good predictive capability, not something that memorizes well only on your training data. Any questions here? Usually when I talk about cross-validation, I basically do, okay, it says the recording has stopped. But you're able to listen to me, right? I see you in the call, so let's go with it. Yeah. Okay, so I want to draw the KFold cross-validation once more. So say this was my input data set. I have divided it into X and Y. X has a lot of columns here. These are my input features. Y is my response or label variable. In KFold cross-validation, say I'm doing 5-fold cross-validation. I divide my input data set into 5 pieces, right? So this is one fold. This is another fold, this is another fold. Every fold has X, Y pairs. So in KFold cross-validation, if K was 5, so I'm doing 5-fold cross-validation. What I do is, I'm just repeating it again. I drop the first fold out and I call it my test set. I train on the rest of the data. Now I have a model. Now, it's very important to remember that when I'm training, I'm passing into my model training both X and Y into the process of learning the model. I'm passing both X and Y. Here I put X and Y aside, but what I now do is I take this model into the prediction phase. So here I'm using this model to predict. Into the prediction phase, what I'm doing is I'm only passing X. I know my Y, but I'm putting it aside. I'm not letting the model know what it is. It will predict what it thinks Y is supposed to be. Let's call it Y hat. Now you know what the true Y is for this particular X. So you can compare the true Y, the ground truth, with what it predicted. If these two are matching very well, the error is you note down here, error 1. Now what you do in the second pass, you bring this back into the data. This and this you are training on. This guy is out. This part is out. So you take this out. You train on these, you predict on this. When you train, you pass both X and Y. When you predict, you only pass X. Then you compare with this part. You get error 2. In the third pass, you drop this guy and you train on this plus these two and these two. The middle guy is out. So you get error 3. Next time you drop fourth guy, you train on the rest. Next you drop the fifth guy, you train on all these and you test on this, E5. You average all these 5 errors. That is your cross-validation error. This is KFold cross-validation. This is what was shown in that cartoon in the slide. This is the KFold cross-validation error. So now what you do, you choose a technique you want to work with, say SVM. SVM has 2 parameters, right? Okay, SVM has 2 parameters. So it can take different values, right? So I can say the parameters are called, say, cost and gamma. Cost would be some number, gamma or some other number. Cost another number, gamma another number. So each box I'm writing those 2 possibilities with a comma, right, before and after. So now what I do is I take one combination of cost and gamma that I want to try. I apply this entire process. I get all E1, E5, I average it, then I get the cross-validation error for that parameter. Then I pass this into the cross. So this is like a cross-validation routine, this whole thing. And then I write down my cross-validation error for this parameter. I write down my cross-validation error for this parameter combination. I try all combinations. And then I see which one gives me the least cross-validation error. Maybe this combination is the optimal. So this particular, maybe cost equal to 70, gamma equal to 3, gave me the least cross-validation error, which means this is the Cost and gamma, if you use, you will get the right amount of complexity of your fit so that you're not overfitting or underfitting, but you're optimally trying to learn the predictive concepts and be able to predict properly on your test data set. So that is the idea. Parameter tuning. All right, so that brings us to the end of the class, but there is one other important slide to show, so let's just show that slide. So there are different kinds of errors we're looking at. Let's assume X is your complexity of the model that you're fitting. Say a model, so whatever parameters choose will decide something on the x-axis with regards to the complexity. So if I choose some parameters that give me low complexity, here maybe I'm at this level of complexity, I'm fitting things like linear regression. Here I'm fitting things like neural networks, support vector machine, deep learning. Even for one particular technique, maybe if I take SVM, for some choice of parameters, SVM is performing very smooth functions. It's not passing through everything. Here at this level of complexity, SVM is passing through everything. So let's assume x-axis is the complexity. Now y-axis is the error. So I'm drawing different kinds of errors. Your training error, as you keep increasing the complexity of your model, your training error keeps on reducing, like we saw. If you pass a very complex model like that zigzag line, then your training error for that SVM will end up becoming 0 based on some choice of parameters, 100% accuracy. That doesn't necessarily mean you'll perform well on your output, on your deployed data set in the future, in real life. The dotted line is a test error. The test error, as you increase the complexity, it keeps on reducing for a while, and then after a while, your error starts increasing. So this is the optimal complexity you want to choose. You want to choose whatever parameters for your chosen technique that gives you this amount of complexity for this particular data set. Because here it is optimal fit. You cannot do better than this in future prediction, right? Because if you choose a model that is smoother and less complex than that, then you're getting a little more error than here. A lot simpler model, you're getting a lot more error. Simply, again, if you're trying to predict a lot more complicated model that seems like going through every point in the data set, the training error is reducing, but in your test data, again, your error is going high. Because it means you have overfitting here. This is the underfitting part, this is the overfitting part. This is the optimal fit. So when we do cross-validation, you try cross-validation, you apply the entire cross-validation process on every choice of parameters that gives you different kinds of complexities, and you measure the cross-validation error, which is trying to mimic the test error basically. And wherever the cross-validation error is the minimum, that is the choice of parameters that you use. Then you have finally tuned or trained your SVM in a machine learning sense, or what your technique is. So this is something that I did in R myself for one particular technique, and I was able to see this behavior. This is from textbook, right? This is from R that I myself did. So I was able to see that behavior, the test set, test error. So this is the optimal complexity that I needed to use. I was using some polynomial fit. I was trying to fit a polynomial instead of fitting a straight line. So the degree of the polynomial is what I want to choose. The line is degree 1, right? So I can fit a quadratic, which is degree 2. I was trying different kinds of, for that particular data set, the degree 1 was giving the best error. So there's no point fitting more complicated stuff. So maybe straight line was being the best. You don't have to fit more quadratic and more complicated curves. Then I'm overfitting. Although my training error keeps on going to 0. It will make me believe that I'm doing good, but when I apply it, it will do very bad. So this is what is optimal fit here, like that. So summary, long list of supervised learning techniques that are available. Every technique has a tuning parameter. We can minimize out of sample, which means predict future performance by tuning the technique with optimal parameters. Tuning can be performed by cross-validation over a discrete grid of parameter combinations. You try cross-validation for all possible combinations and then choose the one that's the best. Okay, so that brings us to the end of the class. Any questions?
Hi, Panis. I want to ask about
Sure.
When we do the model training, like how can we decide what is the right parameter and
Yes. So the only way to decide
is based on experience, or we have to try it a lot and get a basic idea. Oh, this might be the right way to adjust the parameter, or that would be the right way.
Sure. Yeah, that's a good question, right? So very relevant. So the only way you can choose the method you would use is KFold cross-validation. But again, within KFold, since you're trying different combinations like you asked, this is more like a practical trick. What people do is, let me show you. Yeah, let me start here. So say I'm using SVM. You can see what I'm typing, or is it too small? Okay. Yeah, so say you're using SVM. Say I'm telling you that SVM, to use it, you have two parameters, right? I'm saying, say it's cost and gamma. You need to figure this out. So that, and also you're also passing your data in it, right? Yeah. X and Y will be your data. But anyway, parameter-wise, these are the two things you need to decide. So what people do is, first, since you have no idea whether cost has to be small, big, medium, what people do is they try something like e power -1, e power e power -3, let me write it, then I will tell e power -2, e power -1, e power 1, which is e power 0, which is nothing but 1. Then you have e power 1, e power 2, e power 3, so on. You can try more if you want on left side and right as well. So basically, e power -3 means 1 by e cube, which is a very small number. This is very small. Well, here I had a minus. This is very small, but slightly larger than this. Slightly larger. This is number 1. E power 1 is about 2 point something. E power 2 is about 4.5 point something. E power cube is about 8 or something. So it's increasing quicker. So you're going to small numbers to very large numbers. You can try till e power 5. Here you can try till e power -5. Then you're covering very small to very large. Same thing will be your choice of parameters to start with, your first pass for gamma as well. So then your grid is all possible combinations, like a double for loop. You're trying e power -3 cost, e power -3 gamma, e power -3 cost, e power -2 gamma. So everything with everything. Again, e power -2 with everything here. So you're trying like what? In this case, you had 1, 2, 3, 4, 5, 6, 7 possibilities here, 7 possibilities. So you have a for loop of 7 times 7, so 49 possibilities of cost and gamma, right, in this example. And then you will see for each possibility, you will do KFold cross-validation. So you do KFold cross-validation of SVM with each possible cost and gamma that you're choosing here, right? And you'll also give it the data set, of course. So for each possible of these 49 combinations, then maybe one particular combination, then you choose the combination that gave you the least error. So maybe in the first pass, in your particular data set, say cost equal to e power -1, and the gamma equal to e power 2, say for as an example, like a cartoon, gave you the least error. Now the question is, there is a big gap between e power -1 and 1, right? There's an interval of numbers that from very small to very large. Same thing. Between e power 1 and e power 2, there's a big gap of numbers. Then or e power 2 and e power 3. The question is, you want to search between e power 2 and e power 3 because gamma was optimal at e power 2 in your first search, and also between e power 1 and e power 2. So you will try smaller numbers between e power 1 and e power 2, numbers that fall between. So you're zooming in to search more here. Similarly, in your cost, instead of searching everywhere and cost and gamma, cost, you want to zoom around this interval a little more to find finer values between e power -2 or e power -1, where the error will reduce even more. Then you can zoom further. You try that a few times until either your error doesn't reduce too much, so you have already refined enough. When you're changing some decimal point value, then it doesn't matter. But even for small change in parameter, if your error is reducing a lot, there is room in searching a little more. So you keep searching like that until you get an optimal cost and gamma. So that's how you do. So first you're laying a very big net. If you see from very small, like from 0.0001 to, you can go till till 20,000 or 200,000, 2 lakh you're searching. But you're searching in big intervals. Your line, you're searching very big. But after that, your net is where you are finding a good catch. You're zooming in your net more carefully with tighter mesh, basically. That is the more practical process that people do.
Okay, understood. So train the model. Usually, how long does it need to train one, or until we find the right parameter?
How long?
It depends on the data.
Yeah, it depends on the data size and the technique you're fitting. Right, like linear regression is not very complicated, right? Neural networks takes longer for sure if your data set is large, like that. Yeah, it's a trade-off. Okay. I mean, there is no free lunch. People use this word, no free lunch theorem, which means you don't get the best of all worlds. You either get better accuracy with a slower speed, or you always don't get the best of all worlds. Right? It's a trade-off.
Okay, understood. Thank you.
Cool. Oops. Yeah. Any other questions?
Hey Pranit, this question is regarding the assignment. So okay. if I'm reading file in the RStudio, should it be always with .rds extension?
I see. You mean the .r extension or the another extension you said?
.rds, I guess.
RDS? No, not necessarily. If you want to open data, you can open CSV files in R. You can open Excel files. You can open .txt. You can open R data extension. with some
What about the .dat? .dat?
.dat, then you need, usually you need to use read.table as the function.
Read.table. Because I was trying to open the assignment you gave, right, about a file self noise. It was downloaded as a .dat and it was not, I was not able to open it.
Yeah, you can try read.table. And then there will be some
read delim function is also working.
Read which one?
Delim, D-E-L-I-M.
Yeah, you can use, there are multiple functions. Yeah, I agree. You can use that as well. But another thing you need to be aware of is sometimes your data, you don't know if the separator, right? Your separator between 2 points may be just a space. It could be semicolon, it could be comma, right? Comma separator. So sometimes you'll get errors if what it is thinking the separator is by default and what your separator is in the data set. So then you can always check visually and then, oh, separator seems to be semicolon. So then you can say read.table this data, sep equal to semicolon in quotes. So a good way is just whatever function you're using, if it doesn't work, do help of that function. You will know what are possible tweaks you can do.
Okay, and this data file doesn't have any column name. So how do we know which column is regarding what?
It does not have a column name. Is he giving a separate file, like a header file, air
No.
file? No?
No, I didn't see any.
Okay, you didn't think. Okay, so all R will do is it will just take, it will take
First column as the header.
Yeah, it will give it its own names. It will say x1, x2, x3. But one thing you need to make sure is if you do not have a header, when you're reading your file, it will automatically assume your first row of data points is the header, which is not true. That is your values, right? So then you need to say read.table whatever, then comma header equal to false. Otherwise, you lose one row of data. It will call it, those dirty values are, All right, cool. Any other questions? Do try to put some effort on the assignments. I mean, Hemant will keep, trying to take feedback and stuff as well. But in general, it's a good idea. If you have time, do put effort on the assignment. If you aim to do that, if you aim to do some learning hands-on, if your goal was not that, then it's a different situation.
Okay.
Yeah. Okay. Cool. Any other questions? I see. Okay. All right then. Cool. Everyone have a good weekend. There's Thanksgiving coming up next week, so I hope it goes well for everybody. See ya. Bye-bye.
See you, Pranit. Bye.